Hi, I'm João Vitor Freires, and today I'm gonna talk about how to get an exact profile from programs, which is the information about how many times each instruction in the program will be executed. This can be done by instrumenting the control flow graph's edges of a program with some overhead, but some optimizations are able to reduce it significantly, and this is what we're gonna talk about in this presentation. So, let's start with a simple example using the following function that counts the number of zeros within an array. This function can be represented by the following CFG, which contains 6 basic blocks and 7 edges in static single assignment form. Now, in order to retrieve a profile from this function, we want to instrument it by placing counters on each basic block of the function, in such a way that we can get how many times each edge will be traversed, like so. Note that, in order to save the information, we need to initialize the counters for each edge at the start of the function, more specifically at the start of the first basic block of a function. Also, we want to output the information, so we call some output procedure at the end of the execution of the function, which can be achieved by calling this procedure before each return instruction and after the last instruction of basic blocks that don't have any successors. One may notice, however, that the initialization, placement, and output of the counters may introduce overhead in the performance of the code, because there will be more instructions to execute, such as allocs, loads, stores, adders, and so on. In fact, there exists some overhead, so we might want to reduce the number of edges that we need to count, if possible. And actually, it is possible to reduce the number of instrumented edges. One idea for this was introduced by Knuth and Stevenson in 1973, in the paper Optimal Measurement Points for Program Frequency Counts. So first, let's get our program, and from its CFG we will extract the minimum spanning tree, or rather the complement of the MST from this CFG, marked by the red dashed edges. What Knuth and Stevenson have shown is that, by Kirchhoff's first law of flow conservation, by getting the exact profile on the complement of the MST, one can reconstruct the exact profile of the whole program. So, from now on, we will call the instrumented edges KS counters, in reference to Knuth and Stevenson. As a result of this idea, we achieve a lower performance overhead, since we have less load, add, and install instructions. Not only this, these results are optimal in the sense of, if we omit any KS counter, we can reconstruct an exact profile. But we can actually achieve further improvements on reducing the exact profile overhead, not by omitting the KS counters, but by replacing them with something else. Let's get back to our CFG and see something about the region formed by the blocks L6, L9, and LA. Can you notice that every path that reaches this region will do so through block L6? Also, can you notice that every path that leaves this region will do so through block LA? Regions like this in any graph are called single-entry, single-exit regions. In our case, we are interested in cyclic CZ regions involving 5 functions and increments that appear in the data dependency graph of our program. If you don't remember or don't know what a data dependency graph is, I suggest you go watch the following lecture from Fernando Pereira about program slices, where he talks about it. Such regions are called CZ counters and are used in the paper Reducing the Overhead of Exact Profiling by Reusing Affine Variables from Frenot and Pereira 2025. In our program, we have 2 CZ counters, but let's focus on the one formed by the variables sum1 equals to phi of sum0 and sum3. Notice that there is one increment on this CZ counter, on the attribution of sum2. In fact, a CZ counter must contain at least one increment, but can have more, and it's interesting for us that this is the case. The key idea from the mentioned paper is that, once the loop that contains a CZ counter terminates, the profile of this CZ counter is sufficient to infer the profile of every edge of the loop. So, we can replace some KS counters on loop exits with a CZ counter belonging to this loop. Note that, if one loop contains multiple CZ counters, we can use only one of them to infer the loop profile. In this way, we have improved even more the performance of our exact profiling. But there is something else we must discuss, which is the moment where we must initialize and save our information. There are some ways to do it, but I will briefly cover two ways here. First, if we want to get the profile information of every execution of a function, we must initialize at the beginning of the function and save the information at the end of the execution of this function, as discussed earlier. But suppose we have the following program, with a main function and a call to a recursive Fibonacci function. Can you see a problem with the idea of getting profile information of every execution of the Fibonacci function? Take a moment and pause the video if you want to reflect. Remember that every execution of this function will save the information of its profile, and saving means making system calls to either print the information or write a file in the disk, which can be very costly, especially in a function like a recursive Fibonacci where there will be multiple calls to itself. So, how can we save the profile for this program in such a way that we have less information saving procedures? Again, I invite you to take some time and think on a way to solve it. One idea for this is to make use of global variables. First, we get from the program how many counters we must keep information about. Then, we initialize a global frequency array at the start of the main function, like so. Finally, we save the information of the frequency array at the end of the main function as well. In this way, we have only one initialization and one information save for the program. Note that, while this reduces a lot of overhead when compared to the first idea, we have less information of each execution, although the information remains exact. So, that's the end of our talk about exact profiling with low overhead. If you want to know more about it, you can have a look at the implementation of an exact profiler at this repository. Also, if you want to look deep into details, check this paper from Leon Franot and Fernando Pereira, entitled Reducing the Overhead of Exact Profiling by Reusing Affine Variables, where the notion of CZ counters is introduced and some theorems are proven to show that the CZ counters really work.